Greetings everybody. Welcome to the RT Hill Academy course on closed-loop real-time hardware-in-the-loop simulation setup by use of IEC 61850 standard. Our focus in this course is to provide you with valuable hands-on experience running a closed-loop real-time hardware-in-the-loop simulation by using the IEC 61850 standard. So, we keep the theory part as short as possible, and will only teach you the underlying facts that are essential to understand this process. This course will have two main parts. The first part will be a quick recap on the concept of real-time hardware-in-the-loop simulation, and the second part elaborates the use of communication protocols, in particular those defined by the IEC 61850 standard, to set up a closed-loop real-time hardware-in-the-loop simulation environment. So, let's dive into the first part of this course.
As mentioned, part 1 of this webinar will be a quick recap on the concept of real-time hardware-in-the-loop simulation. So, what is real-time simulation? A real-time simulation is a time domain simulation in which the independent variable, that is time, grows at the same pace as the actual time does. Let me show you an example. As you might remember, this figure shows the current flowing through our good old resistor that was simulated in MATLAB Simulink. As the figure shows, the simulation has lasted for 0.1 second or 100 milliseconds. Now, let's have a look at the actual time on the computer when this simulation was running. The actual time on the computer when the simulation started was 8:20 second, and when the simulation finished was 8:20 0.1 second. So, it took precisely 0.1 second for the computer to perform 0.1 second of simulation. Therefore, the simulation was real-time. Now, before we jump into the definition of real-time hardware-in-the-loop, or RT Hill simulation, let's see where a real-time or an RT simulation is needed. Let's assume that you want to Skype with a UFO who lives in a different world. Not just on a different planet, but in a parallel universe where the time runs 2 times faster than it does in our world. That means, for each 1 second that passes in our world, 2 seconds pass in the world of the UFO. So, from your perspective, the UFO would look like a fast-forwarding video, whereas, from the UFO's point of view, you would look like a slow-motion video. Conversely, if the time in the UFO's world runs slower than it does in our world, then, from your perspective, the UFO would look like a slow-motion video, whereas, from the UFO's point of view, you would look like a fast-forwarding video. In either case, you would not be able to properly communicate with the UFO. That would be exactly the case when you interface an actual device with a computer simulation. In this example, the actual device, which might be, for example, a controller or a protection relay, represents you. Likewise, the computer simulation represents the UFO. The time progression for the device is ruled by the time in our world, which is the real time, whereas the time progression in the simulation is governed by the simulation engine. And that can be either faster or slower than real time. So, if we want the device to properly interact with the simulation, we should make sure that the simulation runs in real time. This is where the real-time simulation is needed. And, because the real-time simulation is interfaced with a hardware, the whole setup is called a real-time hardware-in-the-loop, or RT Hill, simulation. You may wonder how the simulation is interfaced with the actual device. Keep in mind that a commercial-grade device is designed to interface with other actual devices in the field. For instance, the device shown in this example expects to receive electric current measurements in the level of a few amperes and voltage measurements in the level of a few hundred volts from current and voltage transformers in the field. The problem is that the analog signals provided by the real-time simulator are limited within a few volts, so a current or a voltage amplifier is needed to scale them up to the level that they becomes meaningful to the actual device. The control signals that are sent back to the simulator may or may not need an interface, depending on their magnitude. You may wonder if there is any other way to implement the interface. The answer is yes. With the advent of communication-based architectures for industrial plants, the devices in actual plants are nowadays interfaced through communication networks, rather than analog or digital signals. Therefore, the real-time simulator manufacturers have implemented a wide range of communication protocols that can be used to interface real-time simulators with the actual devices. This approach is, in fact, the interfacing method that you will learn in this course. Okay, now that we have reviewed the concept of real-time hardware in the loop simulation, it is the time to get started with the second half of this webinar, which explains the use of communication protocols, in particular those defined by the IEC 61850 standard, to set up a closed-loop real-time hardware in the loop simulation environment. Let's start with basics. What is a communication protocol? Imagine two people who are trying to communicate. In order for them to understand each other, they have to understand the same language. This requirement is independent of the physical media that they use for communication, meaning that, no matter what technology they use to communicate, they have to be able to comprehend the same language. That would be exactly the case when two devices are interfaced to communicate with each other. No matter what physical media is used, both devices should be configured to interpret a system of rules that is known to both of them for transmission of information. This system is called communication protocol. In other words, a communication protocol defines the rules, syntax, semantics and synchronization of communication, and possible error recovery methods for transmission of information. There are several communication protocols that are utilized in different industries. Real-time simulators can emulate the industry standard communication protocols to enable the users to perform realistic real-time simulations. Our focus in this course is on two communication protocols that are defined by the IEC 61850 standard for intelligent electronic devices at electrical substations. The IEC 61850 Goose protocol, that is used to exchange information between intelligent electronic devices in a substation over the Ethernet. And the IEC 61850 Sampled Values protocol, that is used to exchange information between measurement equipment and intelligent electronic devices in a substation over the Ethernet. However, before talking about these two protocols, let's quickly review the IEC 61850 standard. So what is the IEC 61850 standard? Introduced by the International Electrotechnical Commission or IEC, the IEC 61850 standard is an international standard that defines an innovative architecture for substation automation. The architecture is implemented by using two key enablers that are defined in the IEC 61850 standard. Semantic hierarchical object data modeling, that is used to describe the data points and the functions embedded in each intelligent electronic device or IED. And communication services, that are used to exchange information between the IEDs themselves, and also between IEDs and the higher levels in the power system management hierarchy. What is the IEC 61850 Goose protocol? The Generic Object-Oriented Substation Event or GOOS, is a publisher-subscriber type communication that is used for information exchange between IEDs in a substation over the Ethernet. GOOS protocol is an event-based protocol. When an event occurs, for example when a trip signal is issued, the triggered IED publishes a message with new data and retransmits it at certain predefined intervals to minimize the chance of message loss. What is the IEC 61850 Sampled Values Protocol? The Sampled Values Protocol is a publisher-subscriber type communication that is used for information exchange between IEDs and measurement equipment in a substation over the Ethernet. The Sampled Values Protocol is used for fast and cyclic transmission of raw data, such as high-resolution sampled point-on-wave data of voltage and current signals. Okay, now that you know real-time simulators can be configured to act as IEC 61850 Goose and Sampled Values Publisher and Subscriber, you can set up a closed-loop RT Hill simulation environment by use of IEC 61850 standard. For example, you can have a real-time simulator simulating your system as well as acting as a merging unit to publish point-on-wave voltage and current data as IEC 61850 Sampled Values messages. On the other side, a protection relay, subscribed to those messages, receives the voltage and current data and publishes a trip signal as an IEC 61850 Goose message when a fault occurs in the system. The real-time simulator, subscribed to that message, receives the trip signal that eventually goes to a few simulated protection relays. And the last word before we close this lecture. Be aware that we, at RT Hill Academy, are setting up a platform for remote access to our RT Hill simulation facility, where the course participants attain hands-on experience running RT Hill simulation. During the hands-on training session, you are supposed to complete a list of real-time hardware in the loop simulation tasks, for which you will receive all needed instructions. Your performance will be evaluated by our instructors once your hands-on training session ends. Finally, upon successful completion of your tasks during the hands-on training session, you will earn an RT Hill Academy Certificate of Completion, a proof that you have knowledge and hands-on experience on the course that you have taken. If you are interested, please sign up below to receive a notification once our platform is launched. Please note that this service will be offered for a fee.
I hope you have enjoyed our lecture on closed-loop real-time HIL simulation setup by use of IEC 61850 standard. Thank you for your attention. Take care and see you next time.